At age 21, Julio began saving $1,200 each year until age 35. That would be 15 payments in an ordinary annuity paying 7.5% annual interest compounded yearly. So he's putting in $1,200 per year into an ordinary annuity paying 7.5% annual interest compounded yearly or annually. And then he will leave that money in the account until he turns 65, and that's 30 additional years. Max begins saving at age 41, and he saves $2,400 per year in this same type of account until he becomes 65, which is 25 payments. Question is, how much does each have in his account at age 65? And we want to round our final answers to the nearest cent. So I would say Max is the simpler case, so let's do that first. He's putting it into the same type of account that Julio is, which is an ordinary annuity. So we'll be using this formula for the future value of an ordinary annuity. And we want to know how much Max has. So it's the same type of account. Notice it says it's the same type of account, which means it pays 7.5% annual interest compounded yearly. Yearly means annually, so that's once a year. And Max is going to leave it in there for 25 years. Once a year payments, 25 payments equals 25 years. So for this particular problem for Max, we know that the time is going to be 25 years. So T is 25. The interest rate is 7.5%, so little r is 7.5%. And it's compounded annually. It's compounded yearly, means annually. So that means that M is equal to 1. Now, given that information, I know that N is equal to 1 times 25. So N is 25. In other words, that essentially gave us N, 25 payments. N is the number of payments over the entire life of the loan. The interest rate, I, is calculated using the formula R over M. And since the interest rate is 7.5%, I want to change it to a decimal by moving the decimal place 2 places to the left. So I get 0.075. And I want to divide it by M, which is 1. So it's very easy to do I here. It's just going to be 0.075. In other words, when the compounding is annually, I and R are the same thing. So now we should be able to calculate this fairly easily. I know that I'm looking for the amount in the account, so that would be capital A. I know that Max is paying in $2,400 per year, so that's capital R. 2,400. And I've already calculated little I. Actually, it was given to us, but you can see where I did the calculation. 0.075 raised to the power of N, which we found out was 25, and then take 1 away from that quantity and divide by little I, which is 0.075. Now let's carry out that calculation. The first thing I want to do is add 1 to 0.75. So if I go to my calculator and take 1 plus 0.075 equal, I get 1.075. Now I want to take that and raise it to the 25th power. So that's where the power button comes into play. I already have the base in the display, so I just hit the power key, then type in the exponent, which is 25, so it'll be 25, and hit equal. That gives me 6.098339613. Looking back at the formula, now I want to subtract 1 from that quantity, so I simply go to the calculator and do minus 1 equals, which gives me 5.0983399613. So looking back at the formula, I need to divide that result by 0.075. So I go to the calculator and say divided by 0.075 equals, giving me 67.9778615. And I think I'll write that intermediate step down. I've sort of just been letting the calculator take care of my intermediate steps, but that's sort of a biggie, so I'll actually write that down. So I won't take 2,400 times 67.9778615. So the only thing left to do to finish getting A for max is to multiply those two numbers together. The 67 point whatever is already in the calculator, so all I need to do is say times 2400 equals, which gives me 163,146.8676. They ask us to do this to the nearest cent, so the nearest cent, that would be $163,146, and to the nearest cent, the 86 is a cent. 7 is bigger than 5, so that's 6 rounds up to 7, so it'd be 87 cents. So if Max put $2,400 a year into this account 25 years later, he would have $163,146.87. So I went ahead and did Max first because this situation was a little simpler. I want to go ahead now and talk about Julio's situation, which is a little bit more complicated. But first of all, keep in mind, I'm putting Max's information up here off to the side so we can use it later. So that's the $163,146.87 that I just got for Max. Now I want to look at Julio's situation. The first thing I'd notice is that I've already done Max. I just want to clear that out of the way and make some more room. So I'm just going to get rid of everything to do with Max temporarily because I don't want to. I've already done it, so I want to get rid of that. I'm just looking at Julio now, and remember, I'm keeping Max's information up here so I can refer to it later because we want to get both. So now we're dealing with Julio. Julio starts off with this ordinary annuity. It says he makes 15 payments once at the end of every year, so it's a 15-year series of payments once per year. So it's an ordinary annuity, so I use my ordinary annuity formula. We're looking for how much Julio has in the account after 15 years. Remember, he's going for 15 payments in this ordinary annuity. So he's putting in $1,200 a year. Little I is R over M, but we calculated that in the last problem. So I'll write it down again, but remember, we've already calculated this. It's 7.5%, so it's 0.075, and it's divided by 1 because he's only putting it in yearly. It's compounded yearly, which means M is equal to 1. So I is equal to 0.075, but that's the same I as in the last problem we just calculated for Max. Now N is M times T. We just decided that M is 1, and he's putting that money into there in that account for 15 years at the end of every year. So T is 15. So for this problem, N is also 15. So I is 0.75 and N is 15. So we plug these things in. So we get 1 plus 0.075 raised to the n power, which we just decided is 15, minus 1, all over 0.075. Now this is a pretty straightforward calculation. I want to add let's just go ahead and get the structure of this down. I want to add 1 to 0.075, and of course I do that by saying 1 plus 0.075 equals. Obviously that gives me 1.075. Next I want to raise that base to a power of 15. Since the base is already in the calculator, I'd use the power button next to the Y and put the power in as 1.5 and hit equal, which gives me 2.958877353. Next I want to subtract 1 away from that, so I'll go back to my calculator and say minus 1 equals, and of course I get 1.958877353. Next I want to divide by 0.075, so I'll go back to my calculator, divided by 0.075 equal, and I get 26.118367. And that's the entire fraction. I haven't been writing down the intermediate steps so far, but that's a biggie, so I'll write that down. That's 26.118367. And of course now I just need to multiply that by 1200, so I'll use my calculator and say times 1200 equals. So that product, which will give me A, is 31342.03764. Now they ask us to round that off to the nearest cent. However, we're not done. In the end, they said round it off to the nearest cent. Since this is just an intermediate calculation, I'm not going to round yet, because we're not done with Julio. That's why I saved it for last. It's a more complicated problem, because Julio is putting that money in, $1,200 a year for 15 years, and then he just lets it sit there. He just leaves that money in the account for another 30 years. So that A there represents how much money Julio had after 15 years. But that money then stays there for another 30. So let's remember that number, but make some more room. This is the amount that I just calculated, but I want to make some more room, so I just push the calculations off. That's the calculation that that's the result of the calculation I just did. But that's just after 15 years. But what happens next is Julio just lets the money sit for 30 more years with no more periodic payments. So we don't have an ordinary annuity anymore. He's just letting it sit for 30 years. There's nothing going on as far as periodic payments. It's just sitting there earning interest. So that means for the last 30 years the account is just an ordinary, just a plain ordinary compound interest account. So that takes us back to the formula when we were calculating just plain old compound interest with no periodic payments. So that tells me that I have to use this formula. A is equal to P times the quantity 1 plus I to the n. That's the formula for ordinary compound interest. I'll move some of this stuff out of the way so I can see better. and have more room to work. So now I've got a little more room to work. So let's just actually do this calculation. We've got to think about what's going on. All of a sudden, the money that was in the account just turns into ordinary compound interest formula, and he has this amount of money sitting in the account when it turns in just an ordinary interest-bearing account. So what happens is the accumulated value becomes the new principal for another 30 years. So that $31,342 and so many cents is the principal for the next 30 years, or for the period beginning the next 30 years. So if I want to calculate how much is in the account at the end of 30 more years, I take the $31,342, and again, I'm not rounding off yet because I'm not at my final result. That's the principal times 1 plus, and I've calculated this little I a bunch of times, so I hope you can remember it's just 0.075 raised to the n power. But this time n is how many years we're in a regular compound interest account, and that's 30 years. So it's raised to the 30th power. Make sure you understand before we go on what's going on. We're taking this amount of money and letting it sit for 30 years at 7.5% interest. That's why we're using that compound interest formula. Okay, so continuing, I want to add 1 in 0.075. So let me write this down and then I'll go to the calculator. I want to calculate 1 plus 0.075 and then raise it to the 30th power. So I'm going to do this all at once. I've been showing every little single step, but I think you can handle this. I'm going to do it all at once now. I'm going to do 1 plus 0.075 equal. That's the base. Then I'm going to hit the power button, raise it to the 30th power, so I do 30 and press equal. So that turns out to be 8.754955189. Now all I need to do is multiply those two numbers together and I'll have the final value of A for Julio. So I do, since the 8-point number is already in the calculator, I'll just do times the other one, which is 31,342.03764 equal. So I get the accumulated value for Julio rounded to the nearest cent as 274,398 point. Now that's 135. So the 3 is the cents place. The 5 is 5 or higher. I round it up to the 3 up to 4. So that would be 14 cents to the nearest cent. Notice I didn't round the intermediate result. I rounded once I got the final result. So Julio's situation more complicated. He put some money in for 15 years, putting in a periodic payment, making that an annuity. We figured out how much he made in those 15 years, and then the amount that came out of that annuity went right back into a regular account with no periodic payments. So it was just a regular compounding account, and that went for another 30 years. And at the end of those total of 45 years, Julio had $274,398.14. Now, just clearing out the calculations and just looking at the result and sort of organizing it better, you can see that from our earlier calculation, Max had a little over $163,000 and Julio had almost $275,000. So the question was, how much does each have in the account at age 65? And there you go. That's the amount for Max. That's the amount for Julio. Julio's was a little more complicated because something happened along the way that changed the calculation.